Hello, I'm Hyunjin Park, a master PhD candidate in the School of Chemical Engineering at Sungkyunkwan University and a member of dual PhD degree program with Nanyang Technological University. Let me briefly tell you how I joined NTU SKKU dual degree program. I first met my advisor at the regular meeting for undergraduate students with professors, and we talked throughout the meeting about his research subject related to pharmaceutical and medical applications. Even though it was very short time, I got my mind just blown by his research because I have dreamed of being a researcher working at pharmaceutical company since I was little. So after the meeting, I decided to join his group, and then he gave me good opportunity to participate in NTU SKKU joint PhD program, which is the reason why I am here as a presenter. Today, I would like to present my project on the topic of protein adsorption onto alumina and silica nanomaterial surfaces, which enables to provide clues for vaccine adjuvant development. I am studying indirect nanoplasmonic sensing platforms utilized for LSPR measurement for biointerfacial science applications, mainly related to lipid bilayer and proteins. This platform consists of metallic nanoparticles deposited on a glass substrate, and the entire surface is coated with conformal dielectric coating. Gold and silver are most commonly employed as a transducer. However, silver is prone to oxidation in ambient conditions. The barrier can be addressed by employing this platform, which motivates us to investigate protein adsorption on sensor surface using silver nanodisk embedded sensor chips. Protein adsorption at solid-liquid interfaces is relevant to various medical biotechnological applications such as vaccine formulation, biosensors, and drug delivery system. Numerous factors can affect protein adsorption behavior, such as protein surface and protein solvent interactions. And evaluation on the real-time adsorption kinetics and the extent of adsorption-related conformational change on the surface is lacking. Therefore, the design of systematic studies coupled with the use of indirect nanoplasmonic sensing platforms are required to investigate such relationships. Bovine serum albumin was selected for the experimental works because it is widely studied as a model of serum albumins and utilized in various biochemical applications. Furthermore, we studied protein adsorption behavior in water organic solvent conditions to investigate how water ethanol mixtures can affect conformational stabilities of proteins at solid-liquid interfaces. Next, we chose alumina and silica as material for surface coating because both materials have been studied for their use as adjuvants in vaccine formulation. And moreover, alumina has different surface charge at physiological pH compared to silica. In other words, alumina is positively charged, while silver is negatively charged. There are the experimental methods used in this study. To determine the size of protein in solution, dynamic light scattering measurement was conducted. Next, localized surface plasmon measurement can detect subtle changes in local reflective index near the sensor surface, which enables to sensitively monitor protein adsorption optics and kinetics. The maximum peak shift indicates the change in reflective index. Schematic illustration showing overall LSPR measurement approach is described here. The peak shift were normalized according to the corresponding bulk reflective index sensitivities of each sensing surface and presented as a column graph here. First, according to the data, there is an increase in the adsorption uptake at higher ethanol fractions on both sensor chips. In addition, the adsorption uptake on the alumina surface is smaller than on silica one for all ethanol fractions due to electrostatic attraction, causing more extensive deformation and in turn less adsorbed BSA molecules on the alumina surface. Next, after the solvent washing step, increase in peak shift were observed for alumina surface in all tested ethanol fractions, while on the silica surface, slight decrease was observed at low ethanol fraction, and peak shift increased only at higher ethanol fraction. This is because for the silica surface, the densification process is contributed only by the ethanol-induced increase in protein conformation flexibility, while for the alumina surface, it is additionally contributed by electrostatic interactions induced by the positive charge on the alumina surface. As you can see here, DLS measurement can reveal that a transition with increasing ethanol fractions results from the changes in colloidal properties from monomer to aggregate at higher ethanol fraction. The overall protein adsorption behaviors on alumina and silica surface are summarized in the schematic illustration. First, BSA protein adsorbed as monomer at lower ethanol fraction. On the other hand, adsorbed as oligomer at higher ethanol fractions. Second, due to additional charge-induced interactions, BSA proteins underwent more extensive deformation on alumina surface, resulting in the decreased adsorption uptake compared to silica surface. After solvent washing, protein odd layer densification was observed across all tested ethanol fractions on the alumina, and only at higher ethanol fractions on the silica because of the presence of additional force. These findings offer the first experimental evidence directly comparing how BSA proteins adsorb, deform, and structurally reorganize on alumina to silica, and offer key insights into their possible adsorption behavior on other aluminum-based salts toward the development of improved adjuvant formulations. Thank you for listening to my presentation.